Hello, so we have reached the course regarding hashing. So in this part, we will discover what's hashing, why we use hashing. We will cover the ADT, the hash table ADT, and then the component of hashing, which are the hash table, the hash function, and collision, and how we resolve these collision. And then we do a small comparison between all these techniques and to end with the hashing technique. So what is hashing and why we use hashing? So we know that we use hashing because it's a useful technique, because we will sort and retrieve information very fastly, and we'll see later on that the complexity of searching an element into a hash table is approximately equal to of 1. So we have already seen that in trees, for example in binary search trees and in heaps, the searching, deletion, and searching for an element is could be done in log n, and in hashing we can do better because we can reach complexity on average equal to O of 1. And it's very useful, and it's mostly used in doing optimal search whenever we want to search for an element and we want to find it quickly. So for the hash table ADT, so obviously we need to create a hash table, we need to search, insert, and delete an element from a hash table. So obviously those are the main questions whenever we encounter any kind of a hash table. So to motivate using hash table, so we have an example here. So we are asking you to give a program, an algorithm, to print the first repeated character if there are duplicated elements in an array. So if we have an array, we want the first duplicated element. So the simple solution is that you need to loop 2 times. So you take the first element and you try to find if it exists in the remaining array, and as far as you go. So you take each element. So you have this array, you take this element and you search the remaining array. You take this one and you try to find, and the complexity is equal to n squared. So how can we do a better solution? So a better solution is that I can loop just one time over this array. I will have another array which will count the number of appearance of each element. So at first, suppose I have this array. So this is the original one. I will have another one that will count the element. So, and since we know that we have the characters and we have in the ASCII table just 256 characters, so we can have an array of 256, and whenever I encounter A, I will increment the cell corresponding to A, and whenever I encounter another A, I will have 2, so 2 it means it's repeated, and I will have the first repeated character. So here is the algorithm, the code. So I have the string, which is the elements, the array of characters. We have the character that we will return, it's the repeated element. So I will declare another array, which is the array of count, which is equal to the number of elements of the ASCII table. At first, I will initialize the counter array to all zeros, and then I will loop over the string, and whenever I'm looping, so I will increment the counter. So if it's equal to 0, it will equal to 1. And whenever I encounter the counter is equal to 1, it means that I have already seen the element. I will return this character and I will end the loop. So obviously I have just done here one loop, so the complexity is around n, and it's way more better than the simple solutions which required n square time. So we are telling you this is possible whenever we know that the set of elements, this is all the characters, so we know that we can declare an element of 256 whatever we repeat the same problem with integers. So obviously I will not declare an array containing the having the size of all the possible numbers of integers, so this is not possible. So there should be another way to map these possible keys to possible solutions. So for that we will be using what's called a hash table. So whenever we call hashing, we need 4 stuff. So we need a hash table, a hash function, and whenever we hash functions or hash elements, there could be collisions, and so we will talk about it, what's collision and how we can resolve collisions. So let's start a hash table. So a table, it's a table. It's like any other arrays. It has indices and it contains elements. So we say that we have keys. So we will store keys in this hash table, and when we have a key, so given a key, so we need to find an element whose key k. We just look at the index k and we find the key. So this is what we call a direct addressing. So whenever we can find a place and we can directly access the element, it's called direct addressing. So if I have a hash table that is big enough that it can contain all the elements and I can directly access this element, it is called direct addressing. So how can we use that? So we'll use a hash table, or we call it hash map. Here in this part we call it hash table. So we'll hash the key and the associated value. So as you can see, there's an S here. It means that for one key there could be multiple values, and for that we will have collisions. So in order to map these keys to the hashing values, we need a hashing function. So most probably, so you know what's a function. So it's a function. It takes an element and it returns a value. So a hash function, it takes a key or an element and it returns a position in the hash table. So let's take an example. So suppose we have three elements, three strings, Khodr, Yunus, and Odile. We have the hash table. So the hash table here, it contains just 13 elements, so from 0 to 12. So in other words, whenever I give these keys, they will return an index either between 0 and 12. So for each of these keys, the hash table, the hash function, will return an index in the hash table, and this is the hash table. So we'll be using a hashing function. So as I will go back, so a hash function, I will give Khodr, and the hash function will tell me a number between 0 and 12. And then I will store Khodr in this index. So the hash function here, we will associate a number between 1 and 26. So this is the hashing function. So I will give a word to the hashing function. The hashing function will do the sum of letter of the words plus number of letter of word modulo 13. So for each letter, for k, so for example, let's do this here. So k, I have here 11 plus h equal 8 plus o equal 15 plus d equal 4 plus o equal 15 plus r, which is equal to 18. It will be equal to 71. And then I will add the number of letters, so they are equal to 6, and all I will do modulo 13 because I need a number between 0 and 12, and I will end with 12. So if I have, so this is the table here from 0 to 13, and I have 12 because it's equal to 13. So in the 12th cell, I would place Khodr. So Yunus, the same, I would place it in 11. And Odile, which look well, they have the same index, so I will put Yunus and Odile in the same cell. So it means they are hashed to the same index in the same hashing table. So as you can see, we have here a collision because we have two elements at the same place. So we need to resolve this, and we will see later how we can resolve the collision. So how can we define a hash function? So you should know that it's not your job to define hash functions. Hash functions are defined by mathematicians because it needs to verify some functions, some properties. So for example, a hash function should minimize a collision, should be easy and quick to compute. We don't need to spend a lot of time in computing the value of the hashing function. It should distribute, this is very important, to distribute the keys evenly in the hash table. So if I have a hash table, I should have keys in all the entries, not just agglomerated in some part. We will see later on that some functions, they have a clustering problem. It means that most of the keys will be in the same place. So this is not a good hashing function, and we will need to use all the information provided in the key. What does it mean, use all the information? For example, whenever we have used here, we hashed the word Khodr, we have used all the elements of Khodr. We have used the K, H, O, D, O, R. We didn't skip any of the characters. Again, so this is very important. We will see later an example of a hashing function that does not use all the information in the key. And the last and important part is to have a high load factor for a given set of keys. So what does it mean, a high load factor? A load factor is the number of elements in the hash table divided by the size of the table. So we need to have this big. So in order to have this big, we need to have the number of elements in the hash table bigger than the size of the table. So it tells in other ways how we are distributing the elements in the hash table. So we will see later on. So now maybe we will not understand it, but whenever we will deal with, for example, a hash table where elements are hashed into linked list, so we need, for example, the elements here, the number of elements here to be relatively low in order to ensure that the complexity is around 1. So we reach the collision. So what is a collision? So whenever we have two information, two records, two strings, or two numbers that are hashed into the same position, to the same location, we say that this is a collision. And in order to, so we cannot deal with collision, we need to resolve the collision. So for that, we have multiple ways to resolve the collision, that we call a collision resolution technique. So whenever we have a collision, so we need to resolve it. So we have two broad types of collision resolution techniques. So either we have the direct chaining or the open addressing. So in direct chaining, we can use linked list, we can use coalesced hashing. So the purpose here, direct chaining, it means that the elements are linked between each other. There's a link, there's another information, so we'll cover that. So in separate chaining, we'll be using a linked list. So you can use BST, a heap, queue, stacks, or whatever you want. It's separate chaining. So whenever there's a collision, I will place the collision element, those that collide, in a separate data structure. For coalesce, I will be using an array. However, I will be using a second attribute in order to link the elements between each other. The open addressing, it means that it's an open, so we have the elements and we need to find another place for the elements that collide, and we will stay in the same array. So we will not be using any external or any we will not chain any other data structure. So we'll cover all these later on, but before that, let's take some examples about the hashing function and how we can find an element into a hash table. So as we have done, in order to add an element to a hash table, so I have the element E, I will hash it, and I will find the index. So the same, I will do it in reverse. So in order to find an element, I will hash it again, and I will look into the index V. So this is it. I will calculate H of E, and it will be V. And then I will check. So if tab of V is empty, so if I didn't find anything in V, so obviously E is not in the hash table, because if tab of V is equal to E, so obviously I will find it. And if tab of V, this is very important, is not equal to E, if there's some other elements, probably E is in the hash table, but it was, because we have these resolution collision techniques, it maybe was pushed away from the current position, and all depends on the technique that we have used. So we will see that in a while. So, and usually, as you see here, we need 1 to 5 axes in order to find whether the element E is in the table or not. So let me give you an example here just to clarify the things. So suppose that I have this hashing table. We have index 1, 2, 3, 4, and we know that the hashing of element B is equal to 3. And I have the hashing of A equal to 3. So I have first A here, and whenever I want to hash B, so there's no place for B, because already the index 3 is occupied. So let's say I have a function that tells me, okay, you can place it on the next empty cell, so I will place it in B. And then I need to find B. I need to find if B is in the hash table. So obviously I will redo the same. So potentially I should find a B at position 3. However, I look here, I find A, and A, it's not B. So maybe, I will say maybe I wanted to add B, but A was there and it may be elsewhere. So okay, I know that I'm using a hashing resolution technique that tells me that whenever I don't find a place for me, I can search elsewhere, and I can try to find the first empty cell. So what I will do is that I will search by looping till on the array and try to find B. So this is the idea, and we'll see later, maybe we'll be using another hashing technique, hashing function, and the things can differ from a function to a function. So Let's take an example of a hashing functions, and we'll see what's wrong with some of these and what we will do with others. So here we consider, so we have the key, so the key is the word like the one we have covered earlier, for example khudar, and we will do here is that every letter is coded over 5 bits. So every letter, for example, A will be coded 0001, B 0002, so you can see it's number 1 in base 2, this is number 2, and so on. So, and for the word, for example, we concatenate these 5 bits together. So this is 2, and this is 1, and this is 3, but all coded in binary. So first we have the function, it's well-known function, hashing function, is called extraction. So in the extraction function, we extract and we concatenate some bit of the word. So here is the hashing function. So we extract just the first, second, 7, and 8 bits. So from any string of bits, I will extract just at most 4 bits, and we will start from the rightmost bit. So this is 1, 2, 3, and 4. So I will have this number, and I will hash the word yet. It will be equal to 8. For example, U, it will be hashed to 13, and B, it will be hashed to 2. So obviously, as we have seen earlier on the characteristic of hashing function, this is not a good hashing function because we are not taking into account all the information in the key, and most probably, as you can see, if I have even if I have bigger words or smaller words, I will not be able to know if the distribution is good here, because maybe I will be ending all the words will end with the same hashing value. So this is not a good hashing function. So I repeat, you are not responsible for the hashing function. So they are mathematicians who provide us with with a good hashing function. There is not a good correct hashing function. There are hashing functions that probably lead to collisions. However, we need to minimize the number of collisions. So we have another example of a hashing function called compressing. So here we'll be using all the bits. So this is a good point now here, and we need to split the word into equal substring. So what I will do that is that for each character we will do the XOR, the auxiliary, the XOR, the XOR between all the elements. So it's exclusive OR. So whenever we do that, so for just a remainder for exclusive OR, so it should be an exclusive OR. So 0 and 0, so let's do it on the other way. 0 or 1 is equal to 1, 1 and 0 is equal to 1, 0 and 0 is equal to 0, 1 or 1 is also equal to 0 because it's exclusive OR. It should be one of two operands is true, not both are true. So whenever we do the hashing function on yet, we end with 3. Whenever we hash on u, we have 3. So for now it's good. However, there's some problem in this function, is that if I have a permutation of a word, for example dad and add, so there's so we'll end up with the same hashing function. So this is not good. So a possible solution is that we can do a circular shift. So we do a circular shift on each of the character, and we will end up with a modified hashing value. So let's move to a third example, which is called the division. So mostly we'll be using this in our examples. So we have a hashing function. So we have a number, a string, or whatever you want, and we'll do just the modulo m, where m is the size of the hashing table. So and we had that also. There's a problem in this hashing function. So whenever m is even, for example, if I'm doing 7 modulo 4, and if I have 8 modulo 4, so if the key is odd, the key would be odd, and if the element is even, so here we have 3 and here we have 0, so the keys would be equal to 0. And if the key is here, the m is odd, so we'll have, so for example 7 modulo 3, so we'll have 1. So again, if 8 modulo 3, we'll have 2. So again, if I have the key are odd, so so sorry, the number of elements in the hash table, or m, is equal to an odd number, and have the keys odd, so we'll end up with odd. And if it's even, I will end up even. So suppose that all the keys are odd, so in the table I will have all the even elements empty. So this is not a good hashing function because it does not distribute all the elements evenly. And for the fourth hashing function, so it's called multiplication. So this function, it was provided by mathematicians. It's the best known hashing function. So it tells us that to hash an element e, we need to do we take e multiple theta, where theta is this value, and then we do the fractional part and we multiply it by m, the size of the hashing table. So and it will lead to of course a hashing index, to an index in the hashing table. So we know that mathematically it was proved that the size of the array is without importance, so it could be 30, 40, 90, whatever you want, and theta, it could be chosen as either this value or 1 minus this value, and it will work. So the proof is mathematical, and we don't care about how this comes. So we just need to implement. It's not our duty to come up with hashing functions. So we have covered some examples. So let's come back, because we need to know, we need to implement, we need to manipulate and see how we can resolve collisions. So we'll start with the open addressing one because it's most easier than the direct chaining one. So let's start with the open addressing. So as you can see, in open addressing, it means that all the hashing elements should be stored in the same table, and it's called closed hashing because we are not using any auxiliary data structure. So it's based on probing. What does it mean, probing? It means that I need to check other places if it's empty or not. So if it's empty, I will place the element. If it's not empty, I will try to find another place. And all the collision also is resolved by probing. So I need to check. The checking depends on the hashing function to check whether there's an empty space. So the first open addressing the collision resolution technique is the linear probing, or called linear search. It means that the probe is equal to 1 and is fixed. It means that if I need to place an element at index I and index I is occupied, I will try to place the element at index I plus 1. And again, if it's occupied, I will try to check I plus 2, and so on. So we'll search the table sequentially from the hashing location and so on. So obviously we can wrap around the table. So if I reach the end of the table, I can start from 0. So the hashing function is like this. So the rehash function, so the hash function, the first hashing function, I don't care what is it. It could be one of the 4 functions that we have covered earlier. So I have the key, I will rehash it, and I will try to find n plus 1 modulo the table of size. So there's a problem here. It's called the primary clustering, which is when we have most of the elements that tend to stuck into the same place. So let's see. So there's no example here. So let's move to the second open addressing one. It's called quadratic probing. It's non-linear probing. So what I will do that the interval or the probe, so here it will increase. So at first it will be equal to 1, and then I will do the power of it. So it will be 4 and then 9 and then 16. So the rehash function is equal to n plus k squared. So let's take an example here. So the first hashing function is key modulo 11. So I have a number and I want to hash the elements into the table. So we know that the table contains 10 elements between 0 and 10 because the m here is equal to 11. So I will take the number 31. So I will hash it. So I will do key modulo 11. So 31 modulo 11 is equal to 9, and I will place 31 at index 9. And then I have 19. 19 modulo 11 is equal to 8, and 8 is empty, so I would place 19 in the place. 2 modulo 11 is equal to 2, and I will place it in 2. 13 modulo 11 is equal to 2, so 2 is already occupied. So what I will do that is I will do the rehashing. So it's n plus k to the power 2. So k now is equal to 1. It's equal to 1 plus, so 2 is the answer here. 2 plus 1 modulo 11, so it's equal to 3. So I will place 13 and 3. So as you can see in the quadratic probing is like the linear probing for the first element, just for the first element. And then I have 25, so 25 modulo 11 is equal to 3, and 3 is already occupied, so now I will try to do that. So n plus k, so k now for 25 is equal to 1, so again I will find equal to 4, so I will place it in 4. 24 modulo 11 is equal to 2. I will try to do that, so as you can see we've already done this here, so it's equal to 3, so 3 is already occupied, so now k for this number is equal to 2, so 2 plus 4 is equal to 6, now 6 is empty, and I can place 24 in 6. 21 modulo 11 is equal to 10, 10 is empty, so I can place 21. 9 modulo 11 is 9, 9 is already filled with 31, so I should probe the next cell, which is here. So here is already occupied now, so I have added 1, now I need to add 4 to this position, so it's equal 1 2 3 4, or it's here 4, so 4 from the first element. So as you can see here we have 9, and then we have here 10, so then we need to add to the first element, it's on n, so 1 2 3, so we have 1 2 3 4 we have here, so 2 is already occupied, now I need to add 9, so from here 1 2 3 4 5 6 7 8 9, so I will place the element here, and this is it. So there's one element here, there should be 5 modulo 11, it will be equal to 5. So you have so you know how we can do this whenever we are using a quadratic probing. So you should know what's quadratic probing. However, the hash function here, it depends on the problem. Maybe we give you another hash function. However, the quadratic probing is fixed, and the linear probing is fixed. The third and last one in the open addressing scheme is the double hashing. So in double hashing we use two functions. So whenever we have a collision from the first function, the probing, so the steps that we need to move, is computed by the second function. So how can we do that? So we'll start, so we should have the second function which is different than the first function. So at first we will start with h1 key, so we will use the first hashing function. Whenever there's a collision, I will use h1 plus h2 of key, and if there's a collision I will multiply it by 2, the second one, and then by 3, and so on. So let's take an example. So those are the two hashing functions, and they are different. The first one is key modulo 11, and the second one is 7 minus key modulo 7. So we'll start with 58. So 58 modulo 11 is equal to 3, and 3 is empty. I would place it in 3. I have 14. 14, it hashes to 3. 3 is already occupied, so I should do h1 plus h2. So h1 is equal to 3, and h2 is equal to 7. And obviously all is modulo 11 because I need to place it in this table. So it will be equal to 10. So I place 14 and 10, and then we have 91. So the first hashing function will tell me equal to 3. The second hashing function, so h1 plus h2, it will lead me to the same value of 10. So again it's occupied. Now I will do h1 plus 2h2. So I will end with 6 here. So I will place 91 at position 6. And then we have 25. So 25, as you can see, it will lead us to 6 here. So after the first collision, so I need to do h1 plus 2h2, and it will end up at index 9. So again, the double hashing should know how it works. So you have two hashing functions, not necessarily those hashing functions, but every time you do h1, and then if there's collision, h1 plus h2, and then h1 plus 2h2, and so on. So those are for the open addressing. Let's move now to the direct chaining. So whenever we tell direct chaining, it means that we will chain, we'll use some extra data structure. So suppose that we have here the keys and there's multiple collisions. So one collision resolution technique is to use linked list. So for example, we have these elements 20 and 100, they hash to the same hashing value, which is to 0, and you can place it in a linked list. It could be sorted or in not sorted or circular list. You can use BSTs here, binary trees, heaps, stacks, queues, whatever we have encountered in the course, graphs, whatever you want. So the second and the last scheme of direct chaining is called Coalesced, and it's one of the most important hashing techniques. So we are hashing the elements in the array. So you should pay attention here that we are not using an auxiliary. However, we are using some other information to tell us how we can link these elements together. So let's see how it will work. So whenever we have a collision between two keys, key 1 and key 2, so obviously and potentially they should have the same hashing value. However, if I have key 2 is equal to V and key 1 is different than V, and we have in V equal to key 1, so look well. So I have key 1 and key 2, they collide, so they have the same V. However, I found in V just key 1 and key 2, so look well, and key 2 is not in V, so it means it is stored elsewhere. So and there should be some information that we need to know. So for each cell we should know that if it's empty or not, and if it's occupied, and we should know if it's correctly occupied or not correctly occupied. So those are the most important information. So we'll see in a while because it's not clear for now. So what we'll do that for each cell in this table, so we'll have two information. We will have data, so the actual key, and the link because it will tell us multiple information. So if in link we have -2, it means that the cell is empty. If there's -1, it tells that there's no link. There's no link, it means that there's no other element that hashes the same hashing value. And if there's an element, it means that we are in the same family, we have the same hashing value. So let me give you just a small example here to clarify. So this is the array. So in each array we have cells. So these are a cell. It contains a data and a link. So let's suppose that the hashing of A is equal to 2 and the hashing of B is equal to 2. So at first all the cells are empty. So in the link we'll find -2, and then I need to add A. So A it's in the index 2. So I would place it here A, and I will say here -1 because there is no one else that hashes to the same hashing value. And then I need to add a B. So B, it will hashes obviously to 2. So here we'll see later, there is a lot of techniques. We can either start from the end, or we can find any hashing function that is suitable for us. So we will cover two categories of stuff, maybe not in the lecture but in the exercise, where we split the array into two parts, the reserved part which is here. So we will talk about it later. But suppose that we place B here, and so I need to link A to B because they hash the same value. So what I will do that I will place -1 here because there is no one linked to B, and I will link A to B. So I will place 6 here. So now I will know that A, so whenever I want to search for B, for example, I will try to find the index 2. So obviously I will not find B here. However, I'll see that, okay, there's some elements. So there are some elements that could be hashed the same function but placed elsewhere. And you can look at index 6. Maybe you can find B. So I will look at index B. At index 6, I will find B, and it's okay. So, and whenever I reach -1, it means that there's no need to continue because this is the last of the elements that they have the same hashing value, which is equal to 2. So this is the idea behind the coalesced hashing. So it's very fast. You will see because we know how the elements are linked. So all the elements that hashes to the same index value, they are linked all together. So in coalesced hashing, so we have a second solution. So so I have told you about it. So we'll consider the array as two zones, a primary zone and a reserve zone. So, and usually the keys are hashed into the primary zone. So again, this is the array. I'll split it into half. This is the primary, and this is the secondary. So obviously all the hashing values should be in between the primary value, and if I have a collision, I try to find a place here to place my collide elements. So you can see that if this one is small, so the reserve part will be quickly filled, and if it's too big, so the elements, yeah, it means that the hashing value should be small, so it will be decreased dispersion effect. So there will not be, so there will be a lot of agglomeration at the end of the secondary part. For the coalesced hashing, we have two types, the leash and ish. So there's just a small difference between these two methods. So let's just cover it. So in the method, for the leash one, so we hash the key and we have the index I, and we start the chaining from position I. So if a k is not found, we'll store the end at the end of the table, of course. So we'll append it to the collision chain. So we have here the hashing function, which is hk equal k modulo 5, and we need to add these 5 elements in sequence. So first I will start from 1. So 1 modulo 5 is equal to 1, so I will place it. 5 modulo 5 is equal to 0 and it's empty. 21 modulo 5 is equal to 1, and 1 is occupied, so I need to place it at the end of the table. So I'll place 25 at 4, and I will link it to 21. So look, well, there's a link between 1 and 21, so as I have told you earlier. And then I have 10 modulo 5 is equal to 0, so 0 is occupied, so now I'll place 10 at index 3, and I will link 5 to 10. And then I have 15 modulo 5 is equal again to 0, so look, well, here, so I have linked 10 to 15. So as I have told you earlier in this example, so this is the leash collision coalesced hashing. So now we have the ish. So in the ish, so there's a little difference on how we are linking the elements. So you will see how. So first we have 1, and 5 modulo 5 is equal to 0. So now it's everything okay. 21 modulo 5 is equal to 1. So look, well, again here there's nothing. And 10, okay. So the problem is here, just the difference is here, is that whenever I'm hashing 15 modulo 5 is equal to 0. So I will not, look, well, here, look for the arrows. So I will not link 5 to 10 and then 10 to 5. This is a leech. For each, what I should do is that I will link it by order on the index of the element. So I will link 5 to 15 and then 15 to 10. So obviously we will not be considering this kind. We will be doing and coding the leash one. So those are the difference. You can take the example here and see the difference between these two addressing technique. So to end this part, we will talk about the comparison of a collision resolution technique. So we'll compare both categories. So we'll start with the linear hashing and the double hashing. So obviously, the choice, it depends on two stuff. First, the cost of computing the hashing function. So the easiest, the better, and the load factor. It means the hash function and how can she distributes the elements over the all indices of the array. And we know that both uses a few probes, and double hashing, it takes more time because I'll be computing two hashing values. To compare the open addressing and the separate chaining, here there's not a real comparison because we cannot compare these two types because they are not the same. So what we can say that is separate chaining, it will use extra memory for links, obviously, if we are using a linked list, or if we are using the coalesced hashing. So there's more information, extra information that we need to manipulate. And in the open addressing, so we need extra memory within the table to terminate the probe sequence. So we know that the open addressing, so we cannot use it if the data does not have unique keys. And for example, if there's some elements that have the same keys, we can use a separate chaining table. So for the open addressing method, so it's between the linear, double, and quadratic probing. So we know that in the probing, it's very fast. Okay, I just need to add +1 and check. The quadratic is easy to implement, and the double probing, it uses the memory more efficiently. So in all cases, they are using a few probes, even if it's linear or double hashing. However, for quadratic hashing, it does not probe all the location of the table because we jump from position to a position. So we have seen also that there are some problems in all these three collision resolution technique. So in linear probing, we have the primary clustering, and quadratic probing, we have the secondary clustering, because we are already doing the same jump whenever we end up with the same index value. And the double probing is complicated to implement. As for the interval, the probing interval in linear probing is fixed, and double probing is computed by another hashing function, and as for the quadratic, is proportional to the hash table. So why we have the hashing table that takes just one as an average complexity? Because of the load factor. So we ensure that each block, for example, each linked list, if we are talking about separate chaining, it has the maximum number of elements less than the load factor. So if we ensure that, we know that we can find the elements in complexity 1. So usually and practically the number of elements in a linked list cannot exceed 20 elements. So it's very reasonable and it could be done in O of 1. So, and we know that if the number of elements in a block, so for example, if the number of elements in the hash in the linked list is greater than the load factor, so we need to rehash the elements into a bigger hash table. So we use a bigger hash table in order to distribute the elements over the whole hash table. So, as for the hashing techniques, we have two types of hashing techniques. So either static hashing or dynamic hashing. It depends on the key. If the data of the hashing is fixed and static, it doesn't change, we will use static hashing. And if it's dynamic, it means if the data is not fixed and it changes from one call to call, so we need an alternative which is called a dynamic hashing that we will not cover in this part. So what are problems that are not suitable for hash table? So if we need to order the elements, so this is not, so we cannot use a hash table. If I need to sort elements, if I have multidimensional data, if I have a data that has, for example, a struct that has multiple elements and I need to work with these elements, so I cannot use hashing. For example, if I have a string, I need to find a prefix. And everything that contains dynamic data that changes, so I cannot use hash table. And for elements that they do not have a unique keys, so again I cannot work with hash table. So this is it for the hash table course. So for the exercises, you can check the link below, and I will skim over the list of exercises. So first we'll have the hashing using linear probing. So it's the regular example. So we have a hash table and we have an index, and we need to insert elements into the hash table, and it's very easy since we are using the linear probing. The second exercise is using the quadratic probing. So again, we need to do the quadratic probing on a regular hash table. For the third one, it's very interesting hashing called Coco hashing. It was a question on the final exam. So, and here we'll be using two hashing functions in order to insert an element into a hash table. The hopscotch hashing, so it's similar to the Coco hashing. We'll use a linear probing technique, which is just some differences. And again, we need to insert and delete some element into this hashing table. So, so here we will we need to trace the adding of an element into a hash table using linear, quadratic, and a separate chaining, where we insert the element at the end of a linked list. So, and then we need to do a hashing with BST. So it's a very common exercises. So instead of linked list, we'll use BSTs. So here we'll be adding an element into a hash table where the hashing is coalesced with separated zones. So it's very important and very nice exercise. So this is what we have told you. However, we'll implement these. The exercise 8. So we need to search for an element. So we have added, we have to search, and then we need to add an element into a hash table with separate chaining. So it's a linked list. So we need here to add an element into a hash table without separated zone. So it's not like this one. So there's no part here. So everything, it goes into each other. So it's very interesting exercise. As for the exercise 11, so here we have also a hashing with BST, but with a modified BST. For exercise 12, it's hashing with queues. And 13 is cycles, where we use a linked list and hashing to find solution to some problems of the linked lists. Hashing with opening addressing, separate chaining, so we'll be using here a BST2. And for the exercise 15, we are using hashing with heaps. For 16, we use some special functions for the collision resolution technique. So obviously it's a kind of quadratic hashing. And this is it for this chapter. So if you have any questions, do not hesitate to write to me and I will answer you back. And again, do not forget to subscribe to my channel and to hit the bell icon to receive all the notification. And again, thanks for watching.